Okay, guys, in this video, I'm going to show you how to find the cross product. So this is another way we can multiply two vectors and also talk about the properties of the cross product, okay? So number one, the cross product, unlike the dot product, is actually a vector, not a number. Okay, and this is how we're going to find it. So we're going to have u crossed with v. This is going to be something called the determinant. Don't worry if you've never heard of what is determinant. I'm going to explain that in a second. And it comes from linear algebra, but this is a way to visualize it. And also, I prefer that everybody finds the cross product this way, okay? Because I will be looking for your work. So we're going to draw this determinant, which is like these large vertical slashes. On the first row, we're going to fill it with standard unit vectors. So this is going to be I, J, K. It's very important for you to show work. So the first row, do not skip it. We're not doing it in our heads. We are writing I, J, K. Then you are going to, in this order, so if it's u cross with v, you're going to put u first. So this is going to be -3, -1, 3. And then follow that by v, -2, 1, 2. You are not, very important, switch order, because actually it can be shown, which we're going to show in a second, that the cross product, unlike the dot product, is not commutative. So if you switch order, you're not going to get the same thing. All right, so let's see what we're going to do here. So first, we are going to start with the start at the top left corner. Take the I vector, okay, so we're going to write I over here. Then we're going to cross the row and the column where I is located. So we're going to cross this row and we're going to cross this column. Okay, and then whatever remains, we're going to multiply by that determinant. It's also called the minor of this element, but it's going to be a determinant which is going to have a size of 2 by 2. So it's a determinant of a 2 by 2 matrix, unlike the original one, which was 3 by 3. So first we do I. Then we're going to move on to j. So move on to j. However, j will come with a minus. So if you're wondering why, this is called an expansion over the first row. Okay, and the way determinants are computed is that you look for the row and the column where the element is located. For example, I is located in the first row or first column. You add up row column, so that would be 1 plus 1, which is 2. If that answer is even, that element will come with the plus. If it's odd, then with the minus. So notice that j is in the first row, second column. So 1 plus 2 is 3. That's odd. That's why j comes with a negative. Okay, so what are we going to be crossing out? Well, we're just going to cross out this time the first row, but this time the second column. And what we will get is this new, what they call minor, or this determinant. Okay, this one right here. Okay, finally, we're going to get to the k. Okay, so for the k, we're going to cross out the first row and the third column. Okay, and then what do we have left? Well, we have -3, -1, -2, 1. So next step is for you to actually memorize. How do you find determinant of a 2 by 2 matrix? This is something that you must know. First, you're going to multiply the diagonal elements. So diagonal elements are like 1, 1, row 1, column 1, and then 2, 2, row 2, column 2. So you're going to multiply these, and then you're going to subtract the product of the other two. So start with the diagonals, like the main diagonal. So this is going to be -1 multiplied by 2. Subtract the product of the other two. Okay, so that's the I. Then it's going to be minus j. Okay, so I'm doing the same exact thing. Let me give myself some more space here. So j, what's going to happen with that? So we're going to multiply these two, right? And then subtract the other two, the product of the other two. So it's going to be -3 times 2, subtract well, subtract -2 multiplied by 3. Okay, so that's jth component. Finally, we'll get to the kth component. So kth component, we multiply the diagonals first. So that's going to be -3 times 1. Subtract the product of the other two. So that would be -1 times -2. Now here you have to be super careful with all these negatives, because this is where people mess up, because there are so many of them. Okay, so there's -2 subtract 3, that's -5. then minus j, and then here we have -6, looks like +6, so that's 0. And then this is going to be -3 subtract 2, so it looks like that's also -5k. All right, so the final answer, let me write it in component form, is -5, 0, -5. How do I know if this answer is correct? So this is something that is actually very important to note, and that is that, and I can show you that later on, but if you have two vectors and you're finding the cross product, so u and v, then the cross product is going to be orthogonal to both u and v. Okay, so the way it's going to be positioned is that this is called the right hand rule. So u cross v, it's called the right hand rule. So you have to curl your fingers from u to v, and then your thumb is going to show you the direction of the cross product, but the cross product will always be orthogonal to each one of them. Okay, so this new vector w, this w, is going to have a 90-degree angle with u and also 90-degree angle with v. All right, so this is going to be like u dot with w, because now it's a dot product, must be 0, because remember, two vectors are orthogonal if their dot product is 0. And also v dot w is also 0. Okay, so what you need to do the check to see if it works. How do I do the check? Take the first vector, so that was -3, -1, 3. Dot it with the answer, and that answer was -5, 0, -5. And you must get 0. Well, let's do that. Compute the dot product. We know how to do that. So that's -3 multiplied by -5 plus -1 times 0, and then plus 3 times -5. So here we've got +15, -15, 0. Now that is not the final thing, not the final check thing, because we just showed that u and the new vector w are orthogonal, but we also have to show the same thing with v and w. So now take -2, 1, 2, and dot it with -5, 0, -5. So what do you get? Well, you get 10 minus 10, which is also 0. Check. So you know that the answer is correct because you checked it. And so that's going to be right here. Now, it turns out that there is another vector that's also orthogonal to both u and v, and that is v cross u. Now, is it going to be the same or not? Well, it actually is not. Okay, so let me show you what's going to happen there. So if I were to do it in a separate question, but this time I'm going to have I, J, K, and this time I'm going to put V first. Am I going to get the same answer? Now, this comes from property of determinants. And the property sounds like this. Whenever you switch rows or columns, the sign of the determinant is going to change. So basically, you're going to get a negative for what you have, meaning that this new answer will just going to be 5, 0, 5, because you just make a minus out of that vector. But let me show you. So for the ith component, you see how you're going to be multiplying this times that minus this times that, right? Which is going to be 3 minus minus 2, so that's a 5. Then for the jth component, we're going to be, well, we're going to be multiplying. Okay, so let me just get rid of this and move it here. We're going to be multiplying that one with this one. And well, we have to multiply this one. Okay, so this is going to be j -6 minus minus 6. So that'd be plus 6. So it can be 0, just like before, right? And then k, you're going to multiply -2 times -1, which is 2, subtract 1 times -3, which is plus 3. So now you see how you get 5, 0, 5. So in conclusion, does it make a difference whether you are crossing u with v or v with u? The answer is yes. Actually, this is negative of that. So they are opposite in sign. So this is the opposite of v cross u. Now, in Calcplot 3D, you can actually see that. It's actually really, really cool. I wanted to show you that real quick. So they have something called exploration, vector explorations. And one of the things they have is the cross product. So if I go to the cross product exploration, so you can see that the cross product, the magenta vector is perpendicular to the red and blue vector. Now, in this case, we can actually vary vectors in 3D. Okay, so we could do that, and then we can just like manipulate them to see what happens. So if I were to move the red vector, move it around, and the blue vector, as you can see, the cross product is still perpendicular to each one, right? It could actually be on the bottom depending on the right-hand rule, right? And then also you can vary the z. You can do that too. So you can actually like grab the vector and make it not necessarily, not necessarily in the z plane, in the xy plane, I mean. So you could do that too. But you can see that every time the cross product is orthogonal, right, to each of these two vectors. So that's something that you need to remember.